Welcome to the AI Accelerator Festival APAC, brought to you by AI Accelerator Institute, with a mission to help develop the next generation of machine intelligence. With expert speakers throughout the agenda, you are in for a treat, covering different industries from healthcare to banking, from retail to manufacturing, from smart cities to autonomous drive. I'm sure you'll pick up loads of learnings and new ideas throughout the festival. If you have any questions during the presentations, please feel free to ask the speakers directly during the live Q&A session, or leave a comment or question during the comment section below the video. We will get back to you on those. If you like our content so far, please check out the AI membership plan, which will give you full access to more exclusive content like framework, reports, podcasts, and more on-demand presentation videos. Please check them out. Also, if you're not a member of our Slack community yet, you should be, which is home to over 3,000 AI practitioners and pioneers across the globe. Here's a link that you can join. I would like to say a big thank you to all our event sponsors, partners, speakers, and all attendees. We cannot do this without you. So now it's the time. Sit back, relax, and enjoy the festival.
AI in the enterprise is all the rage. But put the hype aside. How are today's organizations actually executing and seeing value from enterprise AI? Dataiku is the platform, democratizing access to data and enabling companies to build their own path to enterprise AI. To make enterprise AI a reality, Dataiku provides one simple user interface for data preparation, data exploration, automated machine learning, model deployment, AI monitoring, and management. Dataiku is built for everyone with robust features for both the code-free and the code-first. From business users and analysts to data scientists and engineers, Dataiku makes working with data faster and smarter. Each company's path to enterprise AI looks different, so Dataiku supports the creation of a spectrum of applications. Whether that means building out a self-serve analytics platform or fully operationalized AI integrated with business processes. No matter what the underlying changes in architecture or advancements in technology, Dataiku remains at the center, the cornerstone of data governance and responsible AI. Dataiku's centralized, controlled, and elastic environment fuels exponential growth in the amount of data, the number of AI projects, and the number of people contributing to such projects. Dataiku, for every industry, every use case, and also for everyone. Discover your path to enterprise AI at dataiku.com.
Hello, everyone. Thanks for tuning in. Today, it is our honor to have Aditya here, the lead AI and machine learning engineer from West Pharmaceutical Services. And then he will present a live presentation on explainable AI, making machine learning and deep learning models more interpretable. Aditya, the stage is yours now. Welcome.
Okay, thanks, Ryan, for the introduction. So, hello everyone. I'm Aditya Bhattacharya, and as Ryan has mentioned, we're going to take a walkthrough of the session of Explainable AI, where we'll try to make machine learning and deep learning models more interpretable. But before even we get started, I just wanted to give a quick introduction about myself. So I'm currently working as the lead AI/ML engineer in a 98-year-old pharmaceutical manufacturing company called West Pharmaceutical. And as a part of my day job, I'm currently leading the AI team at West and help to form the AI Center of Excellence at West. And typically in the data science and machine learning domain, I have like about 6 years of industrial exposure around areas like statistical forecasting, computer vision, natural language processing, or even any analytics work with structured data. Okay. And prior to West, I have been associated with Microsoft and Intel. And apart from my day job, I am an AI researcher at an NGO called Must Research, and I'm even one of the faculty members at the Must Research Academy for Data Science and Computer Vision. Now, regarding this session, it's actually going to be on an important topic of explainable AI. And since as and more and more organizations are trusting AI models for making their critical business decision making processes, it is very important for us as AI researchers to make the machine learning models more trustworthy and transparent. Okay. And so I do have a lot of content to cover for this session. So, I'll be taking any questions towards the end, and I'll expect all the audiences to have some kind of basic exposure and understanding of machine learning and deep learning. But if not, it's completely fine. I can take any question and I'll try to answer to the best of my knowledge. But considering the wide diversity of audience, I'll probably not go into too much of depth, but the entire idea is to give some kind of exposure towards the entire world of explainable AI. Okay. So regarding the key topics, we'll first try to understand what is the necessity and the principles of explainable AI and why exactly are we discussing this topic today. And then more specifically, we'll go into the details of model agnostic explainable AI for typical machine learning and deep learning workflows that we generally do. And finally, we are going to talk about certain frameworks which will actually help us to implement some of the ideas or approaches that we'll be discussing for typical machine learning and deep learning models. And last, I would try to end the session with some research questions to consider, certain ideas that might generate certain sparks, which will help the entire community to come up with something which is much better. Okay. So with this, we will get started with the session. So the first topic, as I said, will be to understand why do we need explainable AI? What is the necessity or the principles of explainable AI? So first of all, like most businesses, organizations, or processes even actually consider machine learning models as any black box model where we feed some kind of training data, we train the model, we get or feed new set of data and get certain predictions. Without machine learning, it's like simple rule based applications that we have developed like prior to the era of machine learning and artificial intelligence, right, where we kind of have certain rule groups, we try to write a program out of it, and we try to kind of make the system work according to the rules that we define. But with machine learning, these sort of rules or patterns, we expect the machine to discover by itself, right? We expect the machine to model the entire data that best represents the data and give the necessary output. Okay. But sometimes, let's say, when the machine learning model predicts a certain value, maybe it can be a numeric value or it can be any category, we often don't get the reasoning behind it, right? Like if your machine learning model predicts a certain number, we don't know like why it is saying so, right? And there is no way to actually understand and go back and kind of evaluate why it is saying so. And typically, as I said, since more and more businesses are adopting AI as a part of their decision making process, it is very important for us to even highlight the fact or the reasoning behind the model behaves. Okay. And there can be like multiple consequences of poor prediction. Like typically in very critical applications, let's say maybe going for a bank loan where an applicant has applied for a loan and there is a machine learning based model which is trying to get necessity input from the person, and then maybe just says that you are not or let's say your loan application has been denied, right? But let's say for that person, that loan might be very important, right, for multiple reasons or for multiple need that the person has. So like let's say if the person just gets the final output of what the model is telling, how exactly will the person know that why his application has been rejected, right? So there can be severe consequences related to it. Or even let's say in certain cases where you have a facial recognition system, and based on your current image or current ID card or whatever, your access has actually been denied, considering that your system is kind of wasn't able to recognize you. Then if there is no other fallback plan, then you won't be allowed any access to the premises, maybe of that office or bank or whatever, right? So it can get really complicated, and the consequences of poor prediction can be very high. Okay. And there are like multiple news articles which often talks about some of the problems with AI models or AI algorithms, mostly because of the inherent nature of bias that exists. Now, the thing is, like, algorithms themselves do not have any bias, but it is the underlying data that might have an inherent bias, maybe due to the human beings that who are training them, or maybe the nature of the data that has been collected. And these biases can have like severe consequences. It can have lot of racial related discrimination or gender related discrimination, or maybe it is completely ignoring a certain section of the data population itself, right? And that mostly happens when there is an inherent bias which lies within the data, or the data with which the model has been trained is not holistic enough, like it is not covering every corner of the entire spectrum. Okay, so that's why it's very important for us to understand, like, whatever the model is predicting, there has to be some kind of reasoning behind it, and understanding that reasoning is more and more important nowadays. Okay, so with this we'll try to talk through some of the basic principles of explainable AI, and which tries to cover the entire spectrum of making machine learning and deep learning models more transparent and trustworthy. So explainable AI considers the entire AI model to be traceable. So whatever the model is predicting, we should have a path to go back and understand the main mathematical logic behind it for the final decision making or the prediction that the model gives. Okay, and then it has to be reasonable. So basically, whatever the logic or the prediction that the model gives, there has to be some kind of a reason that should be intuitive enough for a human being to even understand. Okay, and finally, as I mentioned about the understandable AI, so whatever the model is saying, there has to be some sort of sense, like there has to be some sort of uh, interpretability that has to be involved in it, so that the end stakeholders or the end consumers of the AI model should be able to understand that why the model is giving the results that it's giving. Okay, so these are the broad principles based on which the entire paradigm of explainable AI is based on. Okay, now when we talk about different stages of AI explainability, so basically it all starts even before the modeling happens, even before the model is actually trained. So from the data itself, like mostly data scientists and some specialists maybe perform some kind of an exploratory data analysis to understand the data, to understand maybe if the data set has some kind of bias, some kind of common observation, and maybe form certain hypotheses out of the data, which helps the data scientist to even know that like these are the right set of algorithms to model the data. Okay, so this happens even before the actual modeling is done. So this is usually known as pre-modeling explainability. Finally, or maybe next, it comes the explainable modeling, where the models that are used has some sort of explainability kind of inherently built into it. For example, when we talk about any decision tree based model or maybe any linear regression model, these are like quite explainable by themselves. Like we don't need to explicitly describe such models, and they are like inherently explainable. So typically these kind of uh, interpretability life cycle happens during the modeling stage itself, and it's usually called as explainable modeling. And finally, and I would say the most popular approach which the AI research world is focusing on is on the post modeling explainability. Okay, so post modeling explainability makes sure that whatever the results that we get is actually model agnostic. So whatever methods or approaches that we use to draw conclusion from the model prediction is not dependent on the type of model or the algorithms that we use. So that's why it comes under post modeling explainability, where we have certain mechanism like using certain proxy models or surrogate models, certain type of functions or other separate algorithms that we use to draw interpretability out of it. So we're going to discuss about this in more details in the coming slides, but I'm just trying to set the context and give some basic foundations of the topic so that it gets easier for everyone to follow the session. Okay. Now, one thing we need to often keep in mind that there is always a trade-off between accuracy and interpretability. Okay. So as I mentioned, that some of the models are inherently interpretable, like any linear regression, decision tree, any classification based or rule based models. So these are like inherently explainable. We don't need to spend much effort in making those more explainable. But the thing is, like, considering the use case or considering the data set that we will be using, the accuracy of the model might not be always good for those interpretable models. Whereas if we go for certain complicated deep neural network architecture, it is highly possible to get more accurate models, but it gets very difficult to draw any kind of understanding or explainability out of those complicated models. So there is always a trade-off. And the idea is, for most businesses or most business processes where machine learning and deep learning is used, it is always recommended to get a good amount of accuracy beyond a certain threshold, but at the same time, draw some form of interpretability out of it so that the business stakeholders are more confident in trusting what the AI models actually tell us. Okay. Now, whatever we have seen in the previous slide, it's mostly related to kind of a model dependent approach. Whatever the models that we have seen so far, those kind of have some sort of interpretability into it. But as I said, there are a lot of models or approaches which getting or extracting that interpretability is very difficult. That's why most of the AI world is actually focusing on model agnostic explanation methods. Okay. So when we talk about model agnostic methods, these are the top, four or broad four level categories or types of explainability that we try to draw from the inherent data itself. Okay. So one of the categories is called knowledge extraction, which means that from the input data or the output of the model, we try to extract certain statistical or mathematical information to either draw some sort of hypothesis or maybe draw some sort of conclusion what the model is telling. Okay. Again, we are going to see these in more details and what are the typical approaches or techniques used under each of these category to make the models more interpretable. But this is just to give that initial exposure. Okay. Then we have result visualization. I think this is one of the widely followed methods for understanding what the machine learning model is telling. So mostly in result visualization, from whatever the results that we get or the output that we get from any machine learning or deep learning model, we try to pass through another layer of algorithm, or maybe these can be any proxy model or any surrogate model, which are like simpler in nature, which are more interpretable. And from the results, we try to justify whatever the model is telling. So these models can be any similar or like any simple linear models or any decision tree based models, which has like higher level of interpretability. Okay. One of the key important areas in which the research world is working is on this influence based methods. So typically the influence based methods help us to understand what are the key important features or parameters within the model that kind of tries to influence the final decision making process of the model. Like what are the important variables or maybe important amount of changes if we do to a particular variable, then that might lead to a major influence on the final decision making process of the model. Okay. And the fourth one, I would say, is probably one of the methods or approaches which is more closer to bringing explainability to a common person who does not have any understanding of the model, is example based methods, where certain instances of the data sets are used to explain the behavior of the model. So basically we look at certain data points or maybe something which is not part of the training data set altogether, but we try to relate it with back to the training data set and try to say that if we change the new data set or the test data set by a certain degree, then there is a possibility that whatever the result that we are looking for can be obtained. Okay, it will give certain examples or certain reasoning behind why whatever the model is telling, just by taking a reference to the data instance that is involved in it. Okay. Now, typically when we talk about interpretation in a data science lifecycle, as I said, like there are basically three types of explainability methods that are applicable, or stages of explainability that are applicable. But mostly like it is done through either a pre-hoc analysis, where the data scientists do some sort of exploratory data analysis on the data itself to understand the problem, relate the data with the problem, draw some hypothesis out of it, and then then we try to kind of build the model considering the predictive accuracy of the model. But for a common person or for a business stakeholder, the descriptive accuracy matters a lot. So that's why, like, along with pre-hoc analysis, post-hoc analysis is also important, where from the results of the model, we try to draw some sort of conclusions from it. And this, again, itself is an iterative process where we try to take feedback from the business stakeholders and try to improve the descriptive accuracy, or maybe the predictive accuracy, and whichever is more important for that particular use case or problem that is being solved. Okay. Now we are going to see some specific approaches which are used for typical or classical machine learning modeling process, and which are also model agnostic and doesn't depend on the type of model that we use. And whatever the 4 types of model agnostic explanation methods that we have seen, we'll try to see more detailed level of approaches which are taken to implement those. Okay. All right. So the first one, as we discussed, was about knowledge extraction methods using EDA. And I will always argue that exploratory data analysis, or EDA, is one of the most important steps of the entire data science process. Because, like, as a data scientist, I am more interested to understand the data more and just try to understand that whether whatever the data that we have would actually help us to solve the business problem or not, right? So that's why EDA is very important. So as a part of the EDA process, we try to extract certain information from the data, which will help us understand the final performance of the model or final results which the model will be giving us. Okay. So say, for example, when we have 2 types of data set, testing and training, and if the distribution of the data are not same, or if there is some sort of divergence within the data, then that means, like, there is a data drift. So whatever training data that we will be using, when we use the test data set, the models might not be that much accurate, right? So understanding these kind of distribution of the input data set, the output data set, any divergence or data drift between different sets of data, or even if we try to look at this graph, which kind of tells us the distribution of the data for different categories involved, we can clearly see that for some of the minority classes, or let's say for some of the categories which has very less data points, and for some of the classes which have very high data points as compared to the others, there is an inherent chance of the model to be biased on the majority class. Okay, so whatever or how much amount of hyperparameter tuning or model optimization that we do, it is highly possible that the model would be more biased towards the majority class. So if we are not covering the entire spectrum of the data, then our data set or our models will not be that much trustworthy on data sets which are represented in less amount, or something which doesn't have that that much of data to be trained on. Okay, so that's why understanding all these things is very important. Other things that we usually do is doing some kind of correlation heat map, or even when we are working on certain clusters, we try to visualize and see whether the clusters are clearly defined, or maybe even draw some sort of statistical values from the data, like maybe the median value, the range of values, the interquartile ranges, the standard deviation between the data, and so on. Like, these are typical statistical methods that we apply on the data. But the entire idea is to extract as much as knowledge as we can from the input data set itself, to draw certain hypotheses based on which we can justify the results or the outcome of the model. Okay. Now, sometimes this knowledge extraction method is not only done on the input data, it is also done on the output data, where we do something like a root cause analysis. So when we have the results of the model, we try to even break it down, trace back, and go back to the key features used in the model to do some kind of a decomposition tree, which kind of tells us that how important are those features, or maybe the combination of those features, to get the final results that we are expecting. Okay. So these are the key methods which are used in classical machine learning approaches, but there are quite a few used for typical deep learning methods. We are going to see later after this. But moving on to the next one, as I mentioned, result visualization is also one of the popular methods, where whatever the results that we get from the black box machine learning model, we try to have another explainer algorithm. So these are like surrogate models, which are simple models like linear regression, decision tree, or any rule-based models that helps us to understand whatever the model is telling, comes under some of the predefined categories which makes sense or not. Okay, so these are like very easy to implement, but at the same time, and widely used as well. But there are certain models for which getting these visualizations can be more difficult, or whatever the explanation that we'll be able to draw from it might be limited. So that's why we go for other methods also. One of the important ones that I always focus on the understanding the impact of certain feature variables or important features within the data set. So these are typically called influence based methods, where we try to understand the main key features based on which the model is trying to make a decision making process. Say, for example, for predicting diabetes, your blood glucose level, BMI, or even age play a very vital role for making the final prediction. So this has more impact on the data, right? And there is something called sensitivity analysis, which we often do, which means that we try to vary the amount, or let's say vary some of the important variables within the data set by a certain amount, just to see what impact it has on the outcome. Say, for example, in this case, if I increase the blood glucose level values, will it actually help me to understand, or whether the model would be predicting more and more data points as a diabetic or not? So basically, we try to understand the relationship of the outcome with respect to the input key features, and try to understand the sensitivity out of it. So this is usually called as sensitivity analysis. Okay. And similarly, we have something called key influencers, which not only tells us that these are some of the important features, but it also helps us to understand by how much. So basically, let's say if there is a certain variable and it has, like, let's say maybe 2% or 5% chance of impacting the final outcome. So based on that, we try to understand the importance or the impact that it can create by a certain amount. Okay. So these are some of the popular methods which people often use to understand the impact of the models itself. Okay. Now, this is, I would still emphasize that the example-based methods are more important in order to understand the actual reasoning behind the model for someone who doesn't have that much of exposure in maybe the basic mathematics or the statistical reasoning behind the models that we have seen. Okay. So this is called example-based methods, and there is a popular approach called counterfactual explanation. And taking the same loan application example, let's say if someone applies for a loan and the model kind of predicts that the loan application will be denied, then the model also, the whatever the data sets or the parameters that we use within the model, also goes through another counterfactual generation algorithm, which tries to compare between the new data and the data set that has been used to train the model, and tries to give some sort of suggestion as a final output, which makes more sense to a person who is actually consuming the results of the AI model. So in this case, let's say, after the loan application has been denied, if the model gives a suggestion that if the salary of the applicant is increased by 50K, or maybe if the applicant pays the credit card bills for the next 3 months on time, then there is a higher chance that the algorithm would actually approve the loan request. So these kind of suggestions is very important to understand the main logical reasoning of the model for any common person who doesn't have that much of exposure to the typical technical details of the modeling itself. Okay. Now, whatever we have talked so far applies to mostly classical machine learning approaches, but some of these methods are also followed for deep learning based models or approaches. But there are certain additional steps sometimes which are done for deep learning models, especially when we are dealing with unstructured data like images or text or any audio signals and so on. So whenever we are dealing with any tabular data set, it is much easier for us to draw explanations. But whenever we are dealing with any unstructured data, then it gets little difficult, especially when we go for any complicated deep learning model. Okay. But there are approaches, especially, and all those approaches also falls under the 4 categories of explainable methods that we have seen so far. So one of the key approaches which is often used in the image domain when we talk about explanation, and this comes under the influence method, it's called layer-wise relevant propagation. Okay. So when we talk about any deep neural network model, it is always believed that it is the flow of the gradient values from the higher layers of the model to the lower layers if it is maintained consistently, or throughout all the different layers of the model, then the model's performance is much more accurate, and whatever the model gives as an output is more reliable. Okay, so that gradient flow, or the flow of information from the different layers of the model, is something which is very important. Okay, so in order to understand that flow of information, there are typical approaches which are used, and these are some of the popular ones. One of them is called saliency maps. So these saliency maps tries to highlight the important, or it tries to give more weightage, some kind of extra values to the portions of the data which contributes more to the final decision making process of the data. Say for example, here we see, like, in order to predict this dog, this is the region which has like more weightage in terms of the final decision making process of the model. Okay, and similarly, like, we have something called guided back propagation. So like in typical deep learning, I think most of us might be aware of the concept of forward propagation and backward propagation, right? Like, where we will be initializing a model, or the weights and biases which the deep learning model tries to learn, with some sort of initial random values maybe, and then it tries to complete one level of forward propagation to come up with certain value of loss, and based on the loss values that it tries to minimize, it go again and updates the weights and bias. So this backward route, it's often called as backward propagation. So in this case, it is called guided backward propagation because it is a controlled mechanism which tries to pick up those specific points which are actually contributing to the kind of the final decision making process that we are doing, and the final loss functions that are involved in it. Okay, so if you see, like, guided back propagation is probably more reliable in terms of highlighting the specific features, maybe the shapes, some kind of marks, strike marks, or some segments of the image, and tries to tell us that this is the region of the image that we need to see for making the final decision making process. Okay, so similar to the guided backpropagation, we have something called class activation methods, which means that it tries to activate, or it tries to assign some more weightage to certain segments of the image and tries to highlight those. Okay, so this is called a Grad-CAM, a gradient-based class activation methods, which highlights which segments of the image is more important, or the model is looking at these segments of the image to make the final decision-making process. Say, for example, for this dog, it is trying to look at the tail, the face, maybe the shape of the body, and so on. Okay. And similarly, in order to understand the inherent working of the models, we have concepts like layer conductance or layer activation, which tries to even analyze the different layers of the model, or different activation functions which are within the model which are involved. Okay. So these are some of the common influence-based methods which we try to use to understand that what are the key data points that are more impactful for the final decision-making process. Now, as I said, like, for complicated models, it can be very challenging for us to draw interpretability out of it. So whatever the model agnostic explainable methods that we have seen so far, is it also applied for more complex models, like, let's say, transformers or any attention-based models? So it can be possible. So the answer is yes. So this is one example where we see an encoder decoder, an attention based encoder decoder based model was actually applied to on an image. So this is an example of multimodal prediction, where the input was image dataset and the expected output was a caption, or a text based caption that best describes the image. Okay, so here we can clearly see that the caption actually makes a lot of sense. It says that a man riding a bike in the woods. But how do we know that whatever the model is telling from this text data is actually relevant or not? So basically, this is a visualization method. It's called visual attention map, also comes under the influence based method, which tries to highlight a group of pixels or certain segments within the image which relates back to the text output that it has given. So for example, when it is saying a man, it is actually highlighting a like kind of a solid portion of the image, telling that it has only one such segment. So that's why it's telling a man. Like, for the man, it is kind of trying to highlight the entire region of the man riding a bike. Like, even if you see, when it is predicting the bike, it is just highlighting the bike region and not the entire region. And whenever it is telling in the woods, it is highlighting every other region apart from the man and the bicycle, right? So that's why it is able to pick up those relevant details from the image itself and trying to say that whatever the text results it is giving actually makes sense or not. Okay. So the entire idea is even complicated models like any attention based encoder decoder architecture can also go through such methods of explainability and certain visualization techniques to draw explanation out of it. Okay. Now, another important thing which I would also try to argue on is the representation based explanation, where we try to extract knowledge from the input on the output of the data and try to relate it to some human defined concepts. Okay. So this is a popular framework by Google AI. I'm going to talk about it in little more details in the coming section. But this kind of helps us to understand that the main important concepts which a human being would use to explain the nature of the model. So for example, for the zebra, the pattern of black stripes and that white background is very important, right? So the model tries to learn all these kind of representation and tries to explain the underlying functioning of the model from these sort of representations. Okay, so this is called representation based explanation. And there is also something called knowledge extraction using model distillation. So this method is similar to the approach of result visualization using surrogate models, where we try to use a simple model along with a complicated model. But the main difference is here we try to compress the information of a complicated deep neural network model into a simple shallow models, which helps us to understand the results of the model. Okay, so when we talk about compressing the information, we try to extract the information from both the input data which we feed to the model, to the main deep learning model, and even we try to take the output of the model and then pass both to the distillation model or a simple model and then try to draw some sort of explanation out of it. Okay, so it's called interpretable mimic learning, where the main information or whatever the main the logic which the complicated models tries to learn is passed to the simple model, which tries to get simplified across the simpler model, and then we try to do the explanation. This sort of model distillation method or architecture is also often known as student or teacher student architecture, where a teacher is the complicated model which tries to compress the information and pass it to the student, and the student is expected to give the expected results. Okay, now as I said before, during the machine learning approaches also, the example based methods, I would probably say it's more impactful for a common person to understand. So let's say if I have two different images of a bird, and in order to change the first class of the bird prediction that let's say we are doing into the second class, we need to also suggest like what portion of the image should be changed by what extent or by how much. Say for example, in this case we are going to say that the let's say the beak of the bird, the shape of the beak of the bird is different, or if it is increased, or maybe if the color is changed to something like slight orangish, then the class of bird will also get changed into the other one. Okay, so typically this sort of counterfactual explanation helps us to understand what are the features that needs to be changed or modified, and by how much to change the results of the model prediction. Okay, so this is probably more easier for a common person to understand, and these sort of counterfactual explanation are also applicable for complicated deep learning models which works on unstructured data like images. Okay, now so far whatever we have discussed are the key approaches or methods that are applied for both input and output data to draw interpretation or explainability out of it. But now we are going to see some popular frameworks which helps us to understand or implement some of these techniques that we have discussed so far. Okay, so most of the approaches that we have discussed so far can be implemented by all of these 5 frameworks like LIME, SHAP, ELI5, SKATER, and TCAV by Google AI. So typically these methods can actually help us to make our model results more interpretable. When we talk about interpretability, LIME actually focuses on the idea of local interpretation, and it is also model agnostic. And we are going to talk about in more details about it in the coming sections. But we have like other approaches like SHAP. So SHAP is a concept based on game theory, where you have like, it's more like a 2-player zero-sum game where you have 2 competents and which tries to compete against each other. So if one tries to score more points, it will draw some kind of penalty from the other player. Okay, so both tries to score more point, but at the same time both tries to reduce the score of the other opponent. So that's how SHAP values are kind of calculated or based on. Then we have other frameworks like ELI5 or Explain Like I'm 5, which are very simple to use, and it kind of gives good understanding of what are the key features which contributes more to the final decision making. And we have something called SKATER, which is more like a unified framework, which even combines something like Lime and some of the other gradient based methods that we have seen, which help us to understand interpretability at a global as well as a local level. Okay. And finally, we talked about this concept activation vectors or concept based methods, which tries to draw interpretability and relate it to a how a human would think through, right, using this TCAV framework. Okay. Now I'm not going to go through much details about these frameworks, but I will highly recommend all of you to try out these and try to understand the benefit out of it. But I'll try to highlight some key points about these methods. Okay. So for Lime, the entire idea lies that every complex model can be interpretable or can be explained at a linear scale by a simple model. Okay. So which means that, let's say if I have a very complicated model, so at the local scale, we can actually draw certain data points which will help us to understand the entire functioning of the model and which will relate the global working of the model. Okay, so that's why the name also is kept like that, like local interpretable model agnostic explanation. So basically around these local points, it comes up with certain perturb data, like which tries to kind of come up with certain synthetic ways to create the data sets or create certain data points, and it tries to draw a similarity between the discrete data points that it creates with the actual original data points. It tries to create some kind of similarity scores between each, and based on that, based on the similarity score, it tries to draw top features for the model. Okay, now these top features it tries to fit on a linear model which is more explainable and more interpretable. Okay, so Lime is quite useful and can work for both images and as well as text data and even structured data, and it will tell you that what are the key features that are making contribution for the final decision making process of the model. Like this is one example of, I think, COVID-19 data set where it is telling that these presence of maybe something like a chronic disease, certain amount of cold or cough, any respiratory disease or pneumonia might lead to the model prediction to be of COVID-19. And whereas if these values are actually low, it means that it comes under class 0, or that means that person does not have COVID-19. Okay. So it's quite an interesting and important framework. So I'll definitely recommend all of you to try it. But moving on to SHAP values. So as I said, SHAP values considers that concept of game theory. And the main importance of SHAP value is that it not only considers all the features individually, but it tries to consider the additive effect of multiple features together and based on some sort of conditional expectation, which means that if I have 5 important variables and it is highly likely that variable 1 and variable 2 to occur together, okay, then what is the additive effect of it, or what is the total summed effect of both those features or variables to occur together at a higher value. Okay, so these kind of additive effect based on the conditional expectation of the features is mapped clearly using SHAP, whereas for some of the other use cases or other techniques, those try to mostly focus on individualistic variables or features. Okay. Now, again, like from SHAP, we can draw some sort of summary plots, dependency plots, which helps us to understand what is the contribution of that particular variable or collection of variable towards the final decision-making process that we are looking for. Okay. ELI5, as I said, like it's very simple to implement. It can work for both images, text, and even structured data. It tries to highlight the key weights for each of those important features and what is the contribution of each feature for that particular data point or for prediction of that particular data point. Okay, so typically it's very easy to implement and very easy to understand also, and quite helpful, especially when we are going for any structured data analysis. But for unstructured data also, it can be directly used, like for images and for text-based data. Okay. Now for SKATER, as I said, SKATER is kind of a unified framework which combines almost like most of the methods that we have discussed or seen so far. Like for example, from feature importance, from partial dependency plot to understand the impact of the variable, And it also have an integration with the Lime framework, which tells us the extent to which a set of features contribute to the the predictive or the prediction class that it is saying. Okay. Now for TCAV, this is something I would say is relevantly new, and I actually like the idea a lot, especially because it helps us to relate the explanations which a common person can even understand. So the entire idea of TCAV, or testing with concept activation vectors, is that from any complicated neural networks, it tries to draw certain signals and tries to relate based on certain high level concepts which a human being would be using. Say, for example, the color of an object, maybe the gender of an object or of a particular class, the race, the type of the object that it's involved. Okay, so these kind of high level objects it tries to, or high level concepts it tries to relate, or kind of tries to draw some sort of score from the model predictions as well as the data, even though these concepts are directly not involved in the input data set. Okay, say for example, when we are trying to let's say we have a group of pictures from which we are trying to understand whether the picture has an image of a doctor or not, we try to see like what are the high level concepts that define that the person might be a doctor. So maybe a white coat, or maybe a stethoscope, or maybe like based on the gender, like it has been probably observed that 37% of the images might lead to like who are male kind of might lead to a doctor from the data set itself. So these kind of high level concepts it tries to uh, obtain or try to relate back to the data set and draw explanations based on that. Okay, so like the example that we have given, there are certain examples where if in it says that like how much importance, let's say, a race or a gender has on the entire model, even though race or gender might not be part of the initial training or the input data set itself. Okay, and similarly, like like if we talk about other concepts, let's say whenever we are trying to predict whether an animal is zebra or not, even as we human beings will try to describe a zebra as an animal which might look like a horse, which might be white in color with black stripes, and which might be found in maybe areas or locations, geographical locations which are grassy in nature. Okay, so that's why even the model is telling that if the animal has certain amount of stripes, if the animal has certain amounts of stripes, it might lead to a zebra, and zebra might look like a horse, and it is found in savanna or grassy environments. Okay, so typically it tries to learn the concepts from the data, and in order to make the model learn a concept, it needs some examples of that particular concepts, and also like the complementary of it, like certain examples which are not that particular concepts, and it tries to learn on its own. Okay, so it tries to give those concepts and give some importance of, or some kind of probabilistic score on those concepts, and says that based on this data set, if there is higher chance of this concept can occur, and using those concepts it tries to describe the final the final model results. Okay, so that's mostly it of some of the key frameworks, or some of the key methods that are often used to draw explainability or interpretability out of it. But I wanted to end this session with one research question and something to think about that would generate or spark some idea, and maybe some of you can even step forward and work on these areas, which may create a lot of good impact around the entire domain of explainable AI. Okay, so all of these frameworks that we have seen so far, these are actually great, and this can bring interpretability to a great level. But as I mentioned, that as a non-expert or someone who is consuming the results of an AI model who doesn't have a background on mathematics or maybe statistics or some of the technical details, how easy is it for them to understand or interpret the results of the model, right? So they might not have any exposure on mathematics or anything at all, but whatever the results that they are getting, how much easier for them to understand or kind of reason the functioning of the model, right? So that's why it's quite important for us to make the entire idea or approach of explainability as easy as possible, and implement the right level of abstraction which a common person can even understand. Okay, so it's still I would say it's still a developing process which researchers are actively working on, and hopefully we'll get there someday soon. where AI models would be much more useful and much more beneficial for anyone and everyone. Okay. So that's mostly it. And just to give a quick summary of whatever we have discussed so far, we have discussed like why explainable AI is important. And we have also discussed some of the commonly used model agnostic techniques for machine learning and deep learning models. We have also talked about certain frameworks which we can use to make our models more explainable and interpretable. And finally, like as I wanted to leave with this question, that can we evolve explainable AI and extend the explainability to non-expert users as well? Okay. And most of the ideas and concepts that I have referred from is from this book. So this book is very good by Christoph Molnar on interpretable machine learning. So if some of you is really interested, I would highly recommend all of you to go through this book to get more details on some of the topics that we have discussed so far. Okay. So that's it. With this, maybe we can open the floor for any question, like if we have some time.
Yeah, thanks, Aditya. It's a really nice presentation. I can see people have put up a couple of questions here in the chat space. Maybe you can spend a quick 2 to 3 minutes to answer those directly, because we are very quickly to the next one. Sorry about that.
Sure, no problem. So the first question is, what is the mathematical principle behind Grad-CAM? So the entire idea of Grad-CAM is calculating the gradients from the model, from the deep learning model particularly, where we have the gradient calculation, right? When we try to do the back propagation method, and these gradient values are later used for updating the weights and biases. So based on these gradient values, the algorithm or the approach is to assign those gradient values to the weights and try to relate that back to the data. So it tries to highlight certain segments of the image by assigning more weight to it. So basically it tries to activate that, like highlight as an activate that. And then it helps us to understand that those weights or those portions of the image makes more sense for the final prediction of the model. Okay, so completely it is based on the concept of gradient descent. Okay. Is it same as the gradient descent? Absolutely, you're spot on that. So basically it calculates that gradient descent, and based on that it tries to draw the maps out of it. Okay. Next question is, how did you avoid bias in machine learning application? Can you share some tips? Yeah, of course. So definitely the primary step that I often take to avoid bias is by doing a thorough exploratory data analysis, where we try to understand the distribution of the data, what are the dominant features within the data, or maybe the dominant or majority classes within the data, or any kind of any kind of correlation within each of the variables, just to see whether that will add any sort of bias, or any sort of, I would say it will kind of suppress some of the other features within the data. Okay, so that's why EDA is, I would say, one of the best steps that we can take to understand the data itself and avoid bias even before doing the modeling process. Okay. Yeah.
We also got Aruna's comments here.
Yeah.
Thank you, Aruna. It's very important, relevant topic of huge importance and passion.
Yes, absolutely. Explainable AI is very important. And as I said, like more and more business are adopting AI models, right? So it kind of becomes our responsibility to make our machine learning models more interpretable and explainable, so that anyone can trust on it. Like right now, if I trust on an AI model and if the prediction is not good enough, then I would slowly lose trust on it. Then I would kind of lose trust on the entire idea of artificial intelligence, right? So that's why building that transparency, trust, interpretation or explanation is very important.
Sounds great. And for those of you who want to continue the whole conversation and everything, I would suggest to connect with Aditya via LinkedIn. Maybe can they do that?
Yep, absolutely.
I'm pretty sure they can.
Absolutely.
Yeah, and then I think you can just simply put in Aditya's full name and West Pharmaceutical Services. You'll be able to find him. And yes, you can see his email address here in this last PowerPoint slides. Yeah, thanks for the great session. Yeah, a lot of people are loving this. Thank you, Aditya. Sorry, guys, I have to end here for the next session. I hope to get to see you all in the next couple of minutes and the rest of the festival.
Yep. Thank you. Thanks, everyone. Hope this was helpful. Thank you.
Thanks, everyone. Take care.
Thank you.
Bye-bye.
Take care. Bye-bye. Bye. I'll drop